Good morning, all. In today's lecture, we are going to continue with our lectures on linear algebra. We've already done matrix algebra and learned quite many things about matrices. In this lecture, we are going to develop linear algebra because, as I told you, this serves as a formalism for the quantum mechanics. So you must be uh, well aware with the concepts regarding linear algebra, because it will indirectly help you in your journey of quantum mechanics. So till now, what we have done is we have actually seen what are vector spaces. Okay, what are those definitions one needs to keep in mind? What are the what you can say? What are the general rules? You can say what rules must be laid down in order to say that okay, this is your vector space. So I have already stated yesterday that if you some and for vector space, I told you uh, a set V is called a vector space over a field F if it has two operations. One is called as a vector addition, the other one is called as a scalar multiplication. And I will say that this set V forms a vector space if the vector addition, which is defined, uh, which is well defined, whenever you are going to start with vector spaces, the addition operation would be well defined and scalar multiplication would be well defined. Okay, once that you define those operations, this is not necessary addition. Okay, this is not necessary addition. Understand my point? Okay, so understand, sort of vector addition will be defined, that operation would be defined, scalar multiplication would be defined, and once you define them, then you if you find that the vector addition is closed, vector addition uh, uh, is associative, there is an identity element associated with the vector addition. There is an inverse element associated with the vector addition, uh, and also that the vector addition is commutative. Further, for scalar multiplication, with respect to scalar multiplication, this particular scalar multiplication is closed with respect to the set V, and the scalar multiplication distributes over addition, and also that alpha beta times V is equals to alpha beta times V. There should be a unit element, that is 1. If all these properties are satisfied, we say that the set V is the vector space. Yesterday we discussed some of the vector spaces, and today we are going to continue with the same. Uh, let's say first example that I took was R square. Before starting vector spaces, I took an example of R square, and I performed all. I actually made you understand that all these properties are true for R square. And once this is true for R square, we actually generalize this result for Rn. We generalize this result for set of complex numbers, because understand, complex number is nothing but they are ordered pair of real numbers. So you can associate your complex number with the space R square. And since I know that R square forms a linear vector space over R, so therefore we can say that the set of complex numbers also form a linear vector space, right? As I told you, why are we discussing it to this detail? See, as I told you, that the quantum mechanics, the wave functions reside in a Hilbert space, and a Hilbert space is one where you very loosely speaking, a Hilbert space is one where your inner product is defined and it itself is a vector space. So we'll see what is Hilbert space, but that is why this kind of introduction is required. And see, set of all polynomials in X with real coefficients, they also form a linear vector space. Since you know that addition of polynomials is associative, commutative, as well as closed. So if you add the two polynomials, then you will get another polynomial. Okay, and also that 0 being a polynomial serves as an identity element, and for every polynomial there is an inverse element associated. And similarly, you can go on and verify the properties with regards to scalar multiplication. So set of all polynomials with real coefficients form a real vector space. Further, we also took another case of a set of all functions from R to R, and we defined the operation of that is a pointwise addition, that is f plus g is equal to fx plus gx, and alpha times fx is equal to alpha fx, we can say that the set of all functions also form a real vector space. Further, set of all continuous functions also form a real vector space, because you can always take a constant function being a continuous function, you can take zero function as constant function, and zero function being constant function being continuous, so you have an identity there. If fx is continuous, then minus fx is continuous, and you can define the scalar multiplication, and you can verify on your own self that set of all continuous functions on R form a real vector space. Further, uh, we went on to discuss what are subspaces, and subspaces are vector spaces in their own right. Okay, but in order to qualify for to be a subspace, uh, uh, probably that amount of effort is not required. You can go through both of these tests. Okay, and once you go through both of these tests, and if you find that these tests are being are not being violated, you can with all certainty say that your subset v is a subspace. Okay, so for example, if a non-empty subset W of a vector space V over a field F is a subspace of V, then it can only be a subspace if and only if W1 belongs to W. W is what? W is a subset of vector space V. We know that there is a vector space V, and we are actually exploring the W. W is what? W is a subset of V, and V is a vector space over field F. Now, if W is a subspace of V, if and only if W1 belongs to W, W2 belongs to W, and W1 plus W2 belongs to W, capital, and alpha belongs to some field, and W belongs to W, and alpha times W also belongs to W. And similarly, there was another property. And via this, we actually did a few of the questions, and I hope you might have got them. Today also, I'm going to continue with the same discussion, and let us see how much of that you are going to uh, understand. Mostly in physics, you are just required to understand the terminologies. Whatever I'm teaching right now is a little bit over physics. Okay, why it is a little bit over physics? Because as I told you, my intention is to make you your ground very solid when it comes to quantum mechanics. Once your ground is clear, see, quantum mechanics is one of the branch of physics where you'll find that much of the counterintuition would come into place. Okay, so in the words of Einstein, he said that what what is your intuition, or what is your intuition? Intuition is nothing but whatever preoccupations you have till the age 18. They are intuitions, right? And somehow quantum mechanics happens to be quite counterintuitive. So at times, having a physical insight into quantum mechanics is not that easy, but having a mathematical insight to it, okay, that I have found this the solutions for the following potentials. Let's say I'm dealing with the Dirac delta potential. Okay, somehow a physical problem corresponding to Dirac delta potential may not be that apparent to you, but okay, still you'll be able to find bound energy, you'll be able to find the number of states. Okay, so that way quantum mechanics is little bit easier than classical mechanics, because see, in quantum mechanics, even if you don't have some sort of physical understanding, right, I'm not saying you should not have, I'm just saying that initially you don't have, and if you don't have that kind of physical insight, still you will be able to work out through the problems. But in classical mechanics, if you're not able to understand which way the torque is acting, which way the force is acting, or probably which way the pressure is acting, like let's say in thermodynamics, or let's say in oscillating systems, you don't know how the restoring force acts, so you will not be able to make a problem. However, in quantum mechanics, if even if you have certain understanding of okay the framework, then you are able to go through. So that's why if your ground is rock solid, then you're able to excel in quantum mechanics. With this briefly sort of preamble, I want to start with vector spaces all over again. So let us try to find whether the set of all n cross n matrix with real entries form a real vector space. What do you think? There's a set of all n cross n matrices with real entries form a vector space over R. What do you think? Okay, so one of the easier ways to understand this is, see, whatever may be your, let's say, whatever may be your matrix, let's say this is n cross n. Okay, this is n cross n. Just think that how many elements will be there: a11, a12, a13, a21, a22, a23, and so on and so forth. And you will have an1, an2, and an. Okay, so if you write this way or you write this way, this is one and the same thing, right? If I write all these things in this manner, isn't it? It will be element of what? It will be element of r raised to power n square, right? Because total number of elements are what? So there are n square tuples. And you know already that Rn forms a linear vector space, a real vector space. It forms a linear vector space. And so does set of matrices, so a set of n cross n matrices with real entries, they also form a real vector space. They also form a real vector space. Okay. Okay. So today, without wasting time, let us start with a few more questions on vector spaces and your subspaces. Okay. Okay. Now, just think about this. Just let me help myself with the questions and then we'll start. Okay. So just think about all these things that I'm writing on the board and then tell me which of the following forms a vector space. Okay. Subspace, I want to say. So let us say, because this was actually left yesterday. So, okay. What do you think about this? What do you think about this? Let Q dash be equals to Q except 0. Except 0. And okay, not this one. This one would be easy for you. I think let me do a question that is slightly tricky for you. Okay, so try to prove this. This would be easy thing for you. I'm giving you an example. Try to prove this subspace. Okay, before practicing all these vector spaces. For each of the following, subsets W of RQ, determine whether it is a subspace of RQ. Okay. So, and W is a set of x1, x2, x3 in RQ such that option number 1, x1 equals to minus of x2. Option number 2, x1 square is greater than equal to 0. Option number C, x1, x2 is equal to 0. And option number D, x1 plus x2 plus x3 equals to. So all these, we are talking of a subset of RQ, that is one thing. And we want to know that which of the following, for which of the following cases the subset will form a subspace of RQ. We already know that RQ forms a vector space over R. We already know that RQ forms a vector space over R. We want to confirm that which of the following cases qualify the definition for the subspaces. Just trying to do this question. So let us take the first case. The first case says that we are talking of a subset W. We are talking of a subset W such that x1, x2, x3 they all belongs to R, and x1 is equal to minus x2. Okay, so this is it, and we want to know that whether this forms a subspace or not. So see, clearly 0 comma 0 comma 0 indeed would belong to W only. So we can say that W will be a non-empty subset, right? It will be a non-empty subset of R cube. Okay, this will be non-empty subset. Clearly, if I write that minus of 0 is equal to plus of 0, so clearly if I write x2 is equal to 0, so minus of 0 is again plus 0, so it satisfies this condition also, and clearly it would belong to W. So clearly W is a non-empty subset. Now let alpha and beta, yesterday I told you that alpha and beta belongs to field F, so instead of field here we are talking of R. The real number is a field, so R, and let's say we have W1 which is let's x1, then you have this minus x2, and this is this is x3, and you have another one W2 which is equals to what, which is equals to y1 minus y2, and this is y3. Okay, these are two of the things. Now if you just do this kind of operation, alpha W1 plus alpha W2, what are you going to get? You are going to get alpha x1 plus beta y1 minus alpha x2 minus beta y2, and then you're going to get alpha x3 plus beta y3. Okay, and please remember that x1 is equals to minus of x2 here, and here y1, sorry, my mistake, this will be minus y1 and this will be minus x. Okay, and y2 would be equals to what, minus of y1. So y, instead of y2 I have written minus of y1 here, and instead of you can say x2 I have written minus of x1, right? If I write this way, and if I now replace my y2 by minus of y1 and my x2 by minus of x1, right? Is that clear? So if I replace this, I have made a mistake. Okay, so if I replace this, then I will simply get I should have not written this way. Okay, so let me write it in this fashion. Okay, so what am I going to get? I'm going to get just give me a minute. Okay, let me finish this off. Okay, so what am I going to get? I'm going to get minus of alpha x1 here, and here minus of beta y1. Clearly you write this as z2, you write this as z1, you write this as z3. You can find that your z1 is equals to what? It is equal to minus of z2. So your alpha w1 plus alpha w2 is z1, z2, z3, which belongs to R cube, such that z1 equal to minus z2. What does it imply? It implies that alpha z1, alpha w1 plus alpha w2 also belongs to W. It implies what? It implies that W is a subspace. It indeed is a subspace of R cube. Okay. Now just try to do another one. Option number B. What was option number B? In option number B, it was supplied to us that W is a subset where x1, x2, x3 are there, such that x1 whole square was greater than equal to 0, right? Now you see, we understand one thing is quite clear, that okay, so let us take any so you see, Okay, so should I verify that way? Okay, I can verify that way also. Okay, so I know that x1 square is greater than equal to 0, and uh, so you should understand that whenever I'm writing that, okay, I'll write it here. See, whenever somebody writes x1 square is greater than equal to 0, don't write it as x1 greater than 0. No. Okay, understand, whatsoever be the case, whatsoever be the case, if x1 plus square is greater than equal to 0, answer should be x1 should belong to R, because for every real number, the square of a real number is always greater than equal to 0, right? So if I'm writing x1 greater than equal to 0, it implies x1 should belong to R. Yes or no? Please let me know if you are not getting it. So please don't make this mistake that whenever x1 plus square is given to you as greater than equal to 0, quite often I've seen students doing it x1 greater than equal to 0. No, x1 belongs to R would be the solution for it. Because be it anything, you know that uh, anything being squared will give you positive answer only. Yes or no? So what does it imply? It implies this belongs to R. This has got no such constraint. This has got no such constraint. So it implies what? It implies that your W is nothing but your entire R cube only. And we already know that this forms a linear vector space. So clearly, I can say that this is a, you can say a improper subset. What you can say that this is a W is a subspace kind of which, because you already know that R cube is what, you know now, a subset is a set itself, right? So clearly W is a, you can say subspace, you can say entirely, you can say that this is a vector space in its own right. Is that clear or not clear? Is that clear or not clear? Please let me know. Option number third was given to you. I think x1, x2, x3 belongs to R cube such that x1, x2 must be equal to 0. Okay, I hope this is clear. Option number B. Please let me know if it's not clear. If this is the case, will it form a subspace? One thing is very much clear, that if x1, x2 is equal to 0, I can always take x1 as 0. I can always take x2 as 0. So clearly this 0, 0, 0 will always belong to W. So my claim is that my W will be a, claiming that W will be a non-empty subset. It will be a non-empty subset. Now let us go a little bit further and see whether it is a subspace or not. So what should I take? I will take one thing. I know that we have to make this x1 into x2 as 0, right? So I'll take 1 comma 0 comma 0. This belongs to W, right? And I'll take 0 comma 1 comma 0 comma 1 comma 0. This also belongs to W, right? Both of them belongs to W since x1 x2 is equal to 0. But let's say this is your W1, let's say this is your W2. But we know that W1 plus W2 is equals to what? It is equal to 1 comma 1 comma 0, and no longer your x1 x2 is equal to 0. It implies W1 belongs to W, W2 belongs to W, but W1 plus W2 does not belong to W. That implies that these two, so this implies that W is not a subspace. I hope it is clear till now. Or should I repeat it again? Uh, what was option number D? Option number D stated that your W is such that x1, x2, x3 all belongs to R cube, and your x1 plus x2 plus x3 should be equals to 1. Now, if this is the case, then you can I will take one thing. So x1, x2, x3 should be equal to 1. So what I'll do, I'll again take the same example. Let's say 1 comma 0 comma 0. This will belong to W, right? And 0 comma 1 comma 0. This will also belong to W. So let's say this is your W1. This belongs to W. Let's say W2 is this. This also belongs to W. But W1 plus W2 will be equals to what? It will be equals to 1 comma 1 comma 0, and I know that the tuples x1 plus x2 plus x3, their sum would be equal to 2. So clearly w1 plus w2 does not belong to w. It implies what? It implies that w is not a subspace of R cube. Is that clear or not clear? Please let me know in the comments that if there is something that you're not following, and then I'll move further. Okay, so let us move further and do a few more questions on subspaces, and then we will come to the bases and dimensions. Okay, so what do you think about this thing that I'm going to write, and then okay, no responses. Why? Okay, I hope everybody has got. Please let me know. Okay, chalo. If everybody has got everything, then I should move. See, now give me an answer to this. Again, it is the same question that I've already listed. So let's say if this is the case, if I write this way, the same thing that I've written, x1, x2, x3, such that x1 is greater than equal to 0. Such that x1 is greater than equal to 0. Let's say this is your subset. You take it as, uh, okay, you take it as some, let's say set S1. What do you think? Is S1 a subspace or not? Is S1 a subspace or not? If nobody, okay, good. Chalo. So people are getting it now. So that is what I was saying. Okay. So now you see. Okay, so I already taught you the definitions for subspaces. One of the very lenient sort of definition, which is more which is more you can say with more conditions, is that if if I'm saying that W is a subspace of V, then one thing is clear, that W1 belongs to W, W2 belongs to W, and then W1 plus W2 should also belong to W. Secondly, if alpha is an element of field F, then alpha times W should belongs to W. And if third condition, you can also place this condition also. This is another one of the another test you can say for the for declaring a subspace. This subset W contains the zero element, or you can say the zero vector of V. If these three conditions are also met, then also this is a subspace. So two of the conditions I have already taught you. If third condition comes, however, in mathematics we derive that this condition is not necessary as such. But if in case if this comes to a rescue, let's say if I have to prove that okay, the set W does not contain the zero element of V, then straight away I can say that this is not a subspace. So this condition also you can remember. Now, regards this condition, so I know that any element for this, so one of the elements of this would be clearly I can say that x1 you can take it as x1 you can take as 1 comma 0 comma 0. So clearly it is a clearly S1 is a non-empty set. It is a non-empty set. Now you just think of this. Let's say I can take any element from the field F, which is actually R here. So I can take any element from R. Let us take alpha is equal to -1. So this is your x1, and if I multiply alpha into x1, which is 1 0 0, what I'll get? I'll get -1. Alpha is equal to -1. Please do remember 0 0. Does it belongs to S1? No, it does not belong to S1. So if I'm saying that there is an element in S1, alpha times that element should be contained in S1, but it is not contained in S1. Clearly, the first one is -1. Here, to be in S1, your first element should be positive. So clearly, I can say that this is not a subspace. Is that clear? Please let me know, because actually these questions are a little bit different for you. So that's why I'm time and again asking you. Okay, what do you think about this? Let us say there is S2, which contains x1, x2, x3. All these belongs to R cube. I can as well as written it in column vector form, but okay, that's fine. Then an x1 minus 4x2 plus 5x3 is equal to 2. Now, what do you think about this particular? Does it form a subspace of R cube? Does, and I'm writing, does S2 form a subspace of R cube? See, here this statement can come to rescue. This statement, I told you that, let's say here what is the vector space V? V would be your R cube, right? V is your R cube, and S is a subset of R cube, right? Now, if S2 forms a subspace, then it must contain the zero element of V. And what is the zero element of zero vector of V? That is R cube. So we know that 0 comma 0 comma 0 is the zero element in R cube. But does S2 contain 0 comma 0 comma 0? No, it does not. Clearly, see, if I place 0 comma 0 comma 0 comma 0, it will give me 0 minus 4 into 0 plus 5 into 0, which is equal to 0. So clearly 0 comma 0 comma 0 is not contained in S2. So we can say that S2 is not a subspace. Is that clear? Please let me know who all are attending. I don't know. एक मिनट देखो. So I think Anshul is attending. Chinmay is attending, Siddhi is attending. Please let me know if you are getting it or you're not getting it. Okay. Now, let us take another question. This uh, about this. Let's say S3 says that x belongs to R square and y is equal to x square. And what is y and x? So you can take x belongs to R square, x vector belongs to R square. So I should write x comma y belongs to R square. So it will give you an insight. Does S3 form a subspace? Does S3 form a subspace? So let us take example and try to understand. Because see, at times whenever you are in difficulty, take counter example and reject the option. So consider two vectors, -1 and 1, and let us say 1 and 1. Okay, let us take -1 and 1, -1 comma 1 and 1 comma 1. You can see that both of these vectors are actually satisfying this relation. Writing this or writing this one means one and the same thing. Okay, you write this way or you write this way. This is one and the same thing. Okay, so your x is 1, so y is 1. Your x is -1, and I know that y would be -1 square. This is 1. So both of them belong to what? They belong to S3. But -1 1 plus 1 1, it would be equal to what? It would be equal to 0 comma 2, right? And clearly we can see that 2 square is not equal to what? 0. So clearly if w if I say that this is x1, I should say capital X1 and capital X2 belongs to S3, but capital X1 plus capital X2 does not belong to S3. So I can say that it implies that S3 is not a subspace. Is that clear now? Let us take another example, a simple one. Let us take S4 as a matrix of order of 2 cross 2 such that determinant of A is non-zero. Determinant of A is non-zero. Will it form a subspace? Will it form a subspace? What do you think? So clearly it will not form a subspace. Why? See, because we always know that in order that S4 should form it should contain a, basically if 2 cross 2 matrices are there, it contains a 0 element which is 0 0 0 0. And if I add this 0 matrix to, let's say, any matrix, let's say A B C D, then it gives me what? It gives me again the same matrix. Okay, so as I told you that this 0 element here should be contained in what? Should be contained in S4 also. But does S4 contain this? Does S4 contain the 0 element? No, it does not. By 0 element I mean this identity. Okay, so does it contain? No, it does not contain 0, because see, if you take the 0 element, the determinant will be equals to what? determinant will be equals to 0. And we have restricted that in S4 we'll take all those matrices of 2 cross 2 whose determinant is non-zero. So clearly S4 does not form a subspace. Is that clear? I hope it is clear. Okay. Now let us move to another question, which is this. What can you say about this? Last question in this category. Okay, I'll take one or two more, and then we'll finish this off. Okay, let us take this example. Let's say what was that? S4 or S5? What was that? S5. Let's say S5. Uh, S5 contains all those 2 cross 2 matrices such that determinant of A is equal to 0. What do you think? Will it form a subspace? Will it form a subspace? So in order to see that, take two examples. Take example A, which is equal to 1, 0, 0, 1, 1, 0, 0, 0, and take another example B, which is, I think you can take 0, 1, 0, 0. Okay, both of these A and B belong to S5, isn't it? Both of these belongs to S5. But do you think that there's sum belongs to S5? Their sum would be equal to what? 1, 0, 0, 1. And clearly this 1, 0 and 0, 1, the determinant of A plus B would be equals to what? It is clearly 1. So it is not contained in S5. So clearly we can say that S5 does not form a subspace. Okay, so please remember all these things. That is these information are very valuable for examination. Directly somebody may ask another questions. Let me give you those questions also, so that you don't make them you don't put wrong answer to them. Just give me a minute. I'll jot down those 2 points also. With regards to Hermitian matrices, please remember, because again Hermitian matrices are those matrices which we shall see in our quantum mechanics course quite often. Okay, so always remember, I'm writing 2 notes here, small. So the first note is that if we are considering V to be a set of n cross n complex matrices, with usual matrix addition and scalar multiplication, and let's say W be the set of all Hermitian matrices. W be the set of all Hermitian matrices of order n. Okay, now this particular W forms a vector space. It forms a vector space only when the scalars are real. So W, it will be a subspace of V. So W forms a vector space only if the scalars are real numbers. Scalars are real numbers, and if they're complex, then they will not form a vector space. Let us take an example and understand. So let us take an example and let us understand that. Okay, let us take an example. So let's say A is one of the example where your A is equals to A x plus iota y, you have x minus iota y, and you have B. This all belongs to W. Fine. Now if I take alpha from a complex number, let's say I take a alpha from complex number, and let's say alpha is equal to iota. This is quite clear. This is Hermitian. This is quite Hermitian. You can say that you take A conjugate and then take a transpose to it, you will get A only. So this is a Hermitian matrix. Right. Now, if let's say this is your you can say that this is your W1 which belongs to W, then if it is a subspace or it's a vector space in itself, then the iota W1 should also belong to W, right? But we know that iota W1 will be equals to what? It will be equals to A iota, and here you will have X iota minus Y, and here you will have X iota plus X iota plus Y, and here you have B iota. Clearly it does not belongs to W. So always remember that if you're given Hermitian matrices of order n, let's say V is a set of n cross n matrix, like n cross n complex matrices, a set of n cross n complex matrices, then W forms a vector space in itself, or you can say W forms a subspace of V only if the scalars are real number. Otherwise, it will not form. Is that clear or not clear? I hope everybody is getting the point. Today, I don't know. Only Siddhi is answering the questions. What about others? Anshul, are you getting the point? Are you not getting it? Okay, so Anshul is not attending the class, I guess. Okay. So now let us move to something very important, which is called as the linear combinations. Which is called as the linear combinations. Okay, so let us move to linear combinations. Okay, linear combinations. Achha, before I move to this, please note down a result that always remember that this, if you remember, whenever you used to write subsets, collection of subsets, then we used to always say that a void set is a subset. A void set is a subset always. So clearly, I can write that this you can say 0. That this null is, you can say that what you can say that this particular space which has what you can say a 0 is a subspace of the vector space V over F. Always. It is always a subspace of the vector space V over F. See, because it satisfies one thing. Clearly, it contains a 0. So I can say that this is a non-empty set. Clearly, it is a non-empty set. Secondly, if you just add 0 to 0, that is, if W1 is only, this is the element, so W1 plus W2, again you will get at 0, and which is again contained in this singleton, or what you can say. And also, if alpha is any field, you multiply it with alpha belongs to any field F, and alpha times 0, again you will get 0, which is again contained. So always remember, trivially, this is a subspace of the vector space V over F. Now let us move to something called as linear combinations. See, just understand, when we were discussing R square, or let's say R cube, when we discuss R square, or let's say R cube, that is 2-dimensional space and 3-dimensional space. That is, in 3-dimensional space, we know that the vectors are called as the space vectors, and in 2-dimensional space, the vectors are called as the plane vectors. In both of these spaces, we can know that you give me any vector, I can always write my vector in 2-dimensional space in terms of the, let's say if it is in the xy plane, then I can write it in form of, I cap and j cap. And let's say if I'm in a 3-dimensional space, any vector can be written in form of I cap, j cap, and k cap, right? So basically, you can generalize this kind of statement, and let's say if v1, v2, v3 and vn are elements of a vector space, v over f, and alpha 1, alpha 2, alpha n belongs to field f. Then the vector alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 dash 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 alpha n vn. This is called as the linear combination. This is called as the linear combination of v1, v2, v3, vn, or at times this is referred to by the set this. If I say this, I mean that I'm referring to the linear combination of all these vectors. I'm referring to the linear combination of these vectors. If I'm writing in this curly braces notation, I am implying that this particular notation itself implies that I'm referring to linear combination of v1, v2, v3, vn. Always remember that this particular set, you can say this particular set. After all, this will belong to what? All these vectors when added will again, so let's say v1 is a two-dimensional vector, this is a vector in two-dimensional space, this is a vector in two-dimensional space, this is a vector in two-dimensional space. All these things when added will again be a vector in two-dimensional space only, right? And if I multiply it with some alpha or beta something, then again it will belong to that two-dimensional space. So you can say that this alpha 1 v1 plus alpha 2 v2 dash dash alpha and vn, where alpha i's are some scalar, or you can say alpha i's belong to some field f. This particular subset, let's say W, forms a subspace of V. Forms a subspace of V. Is that clear? Okay. Further, if you think, let's say, if I'm talking of r cube and r square, and if I generalize this statement to Rn, I know that any vector in Rn can be written as linear combination of E1 cap, E2 cap, dash dash dash, En cap. Okay, and what is even? Even cap is 1 comma 0 comma 0 dash 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 0. This is having n tuples. E2 is what? It is equals to 0 1 0 0 0 dash 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 0. And what is En? So on and so forth. I can write this as 0 0 0 dash 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 and last number. Okay, so all these what we say that all these things are all these elements, that is 1 0 0 0 1 0 0, I can write any vector in Rn in form of these, right? In other words, what we say that these set, that is E1 E2 E3 dash 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 En, all these you can say unit vectors spans Rn. In other words, we say that this spans Rn. That is, if you can write any vector in Rn in form of all these unit vectors, that is E1 cap, E2 cap, E3 cap, dash 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 En. Similar things you can write it for R square and R cube. So basically, I have generalized this. So this brings us to a definition of linear span. I hope till now everybody is getting the point. Please let me know in the comment section whether it is understandable or not understandable, because from here on the things are going to get a little more rigorous and probably more useful for your physics part. Please let me know. Is that clear? Please let me know. Okay. Okay, so I should move further. Oh, so this is one thing. Now this brings us to definition of linear span. What is a linear span? See, I'm writing it formally here. So let V be a vector space. Let V be a vector space over field F, and let S be a subset of V. The linear span of S is defined as what you can say, all the linear combinations all the linear combinations all the linear combination of a finite number of elements of S. It is denoted by square bracket S. So if I'm writing this, I want to write that this represents my span. And basically, what does it mean? It means that what comes in span? In span comes all the possible linear combinations. So all the possible linear combinations I'm going to write here. All the possible linear combinations. And alpha i's belong to. Okay, so this represents the linear span, and we say that S generates, that is S, these uh, these are what? These are subsets of V, and these generate what? These generate the total linear span. We actually say this way. Okay, let us say that suppose for two dimension, let's say, what would be linear span? So I know that. Let me take. What do you think in two dimensions? What are those two vectors which can generate the entire space? Just think about them. What are those two vectors which can generate or which can span the entire R square? Clearly, I can write those will be 0, 1 and 1, 0. So clearly, this I can write them as S. So my S is a subset of R square. Yes or no? True. From R square, I'm just choosing these two elements, that is 1, 0 and 0, 1. Can this S span the entire space? Yes, it can. You write the entire R square. In terms of, you can write entire R square in terms of these two, 0, 1 and 1, 0. So in other words, I can say that my elements 0, 1 and 1, 0, they span R square, or I can say they generate the entire R square. And what would be the linear span? Linear span was what? Linear span was all the possible linear combinations that you can form with these set S. So they will be what? Let's say alpha belongs to R. Let's say beta belongs to R. Then I can write alpha 0, 1 plus beta 1, 0, where alpha beta belongs to R. This is your linear span. So you can really write it as beta, alpha. So this is your linear span. This is your linear span. Is that clear? So for example, it's not that only every time you have to define these standard ones. Okay, you can take another ones also. Let's say let us say for R cube, we can say, let us say that set S contains 1 comma 1 comma minus 1. So what is the linear span of S? Linear span of S will contain all the possible linear combinations of this, all the possible linear combinations of, so this will be simply this, sorry, 1 comma 1 comma alpha belongs to R. So this is your linear span. Linear span is all the possible linear combinations that you can make from the set S. So this is the linear span. Is that clear? Now just give me an answer to this question. Just give me an answer to this question. Let S be defined as 1 comma x comma x square, and this is a subset of set of polynomials. Be a subset of set of polynomials. If you remember, we denoted it by simply p. The question is, does 2x plus 3x cube is contained in the linear span of S? Do you think that it is contained? Just mark the answer yes or no in the comment section so that I can understand that you are getting it or not. Please do it. So clearly, if this is the set S, then the linear span of S would be what? It would be equals to some alpha x square plus beta x plus gamma, where alpha, beta and gamma belongs to R. Do you really think that alpha x square plus beta times x plus gamma can generate any time 2x plus 3x cube? Can there be a power of x cube? No, not at all. The highest power that the linear span can have, the degree the linear span will contain, the highest degree that linear span would contain is 2, that is quadratic. It can never have this kind of term. So clearly, this is not, clearly 2x plus 3x cube is not contained in set S. This linear span of S. Is that clear or not clear? Please at least give me an feedback that are you getting the point or are you not getting the point? Okay. Now, just now take some examples to understand linear span. Okay. Then we'll move to bases and dimensions. And almost every year you will find a question in GATE exam regarding the dimensions of the Hilbert space. Okay, so this is like quite often now they're asking. Also, there are a few theorems that I want to mention, and I will not write them up as such. Just remember that if S happens to be a non-empty subset, of a vector space V over field F, then this linear span of S is a subspace of V. Is a subspace of V. Just remember this as a result, clearly. And if this non-empty subset vector space V happens to be a subspace itself. So if S happens to be subspace, then S is equals to linear span. I mean, these two are very like we have to prove them. Right now, I'm not in a mood to prove them right now because see, in physics we are here to just know things up. Okay, so just remember these two results. Uh, they may be useful at some point of time, and I'll use them directly there. Okay, now let us consider a few questions to so that you can make hold of your concepts. Okay, the question is, let S be uh, a subset which I'm writing as 1 comma 1 comma 0 comma 2 comma 1 comma 3, and this is a subset of R cube, right? This is a subset of R cube. Uh, we want to determine which of the following vectors which I am going to write are in the linear span of S. So which of the following vectors are in linear span of S? So let us say the option number 1 is 0 comma 0 comma 0. Option number B is 1 comma 2 comma 3. Option number C is 4 by 3 comma 1 comma 1. What do you think? Which of the following vectors are in the linear span of S? Please do remember linear span of S. S I have already mentioned. This is your S. And you have to see which of the following vectors are in the linear span of S. See. So what would be the linear span of S? The linear span of S would be simply alpha times 1 comma 1 comma 0 plus beta times 2 comma 1 comma 3, right? And where alpha and beta belongs to R. Where alpha and beta belongs to R. Okay, so this linear span, I can write it as alpha plus 2 beta comma, what can I write? I can write alpha plus beta. Okay, and then the last one would be simply 3 times beta, right? Where alpha beta belongs to R. So this will dictate your linear span, right? I mean, this is your linear span. Now, if this is your linear span, the question is asked that which of the following vectors, like A, B, C, are in linear span. So let's say the first one, that is 0 comma 0 comma 0, is in the linear span. So for that to be in linear span, alpha plus 2 beta should be 0, alpha plus beta should be 0, and 3 beta must be 0. Right? So what does it imply? It implies 0, it implies alpha equal to 0, okay. So what does it imply? It implies, okay, that was very much the case, right? So that we could have taken any way out. That we could have taken any way out. See, why we could have taken it any way out? See, understand what is alpha? Alpha belongs to R. What is beta? Beta belongs to R. Okay, both of them belongs to R. Both of them belongs to R. So I can write this alpha plus 2 beta as x1. Alpha plus beta is, let's say, x2, and 3 beta is x3. So your this linear span S is nothing but x1 comma x2 comma x3, where all of these three things are what belongs to R. So that implies this is nothing but this is R cube, and if it is R cube, I can say that this forms a subspace. Okay, it forms a subspace. If it forms a subspace, then it should contain the identity element, or it should contain the identity element or zero element. It should contain the additive identity, right? Or the zero element. It should contain the additive identity of R cube, and clearly it contains the additive identity, because 0 comma 0 comma 0 is what? It is the additive identity in R cube. So if this linear span, indeed, what is linear span? After all, it is alpha plus 2 beta, alpha plus beta, and 3 beta. Beta belongs to R, so 3 times beta belongs to R. Alpha plus beta belongs to R. Alpha plus 2 beta also belongs to R. So basically, this linear span is nothing but it is R cube only. And R cube, being a vector space, should contain additive identity. And if it contains additive identity, it would contain 0 comma 0 comma 0. So option number 1 is indeed correct. I mean, we don't even need to check it. Is that clear? Uh, is that clear or not clear? Please let me know. Whosoever is actually right now there. I think Siddhi is there. Please let me know, Siddhi, is that clear? Okay, so what do you think that whether alpha, this thing will be 1 comma 2 comma 3 would be there in the linear span. So in order that 1 comma 2 comma 3 should be there in the linear span, then alpha plus 2 beta should be equals to what? 1, alpha plus beta should be equals to 2, and 3 beta should be equals to 3, right? Only then I can say that this is contained. So if 3 beta is equal to 3, that means what? Beta should be equal to 1, and if beta is equal to 1, then alpha is equal to 1, right? If beta is equal to 1, then alpha should be equal to 1. But if beta is equal to 1 and alpha is equal to 1, then alpha plus 2 beta would be equal to what? 3, and it is never equal to 1. So clearly these three are not simultaneously satisfied. So I can say that 1 comma 2 comma 3 does not belong to the span of S. It does not belong to the span of S. What is span of S? I'm reiterating. Linear span of S is all the possible linear combinations. Okay. Now, when you're making all the possible linear combinations by using these two vectors, that is 1 comma 1 comma 0 and 2 comma 1 comma 3, the question that is asked that whether this particular span would contain 1 comma 2 comma 3. So answer is no. Because if it had to contain 1 comma 2 comma 3, then beta should be equal to 1, alpha should be equal to 1, and alpha plus 2 beta should also be equal to 1, which indeed is not getting satisfied. So all these equations are not getting simultaneously satisfied, implies that 1 comma 2 comma 3 is not contained in the linear span of S. Is that clear? I hope it is clear. And C option, what would be? For C option, that is 4 by 3 comma 1 comma 1 to be in the linear span of S, I'm writing it here. For it to be in the linear span of for it to be in the linear span of S, 4 by 3 should be equals to alpha plus 2 beta. 1 should be equals to what? Alpha plus beta, and 3 beta should be also equal to 1. So if indeed this is the case, okay, I'm so sorry because actually there was a network issue. Okay, now you see, okay, so sorry for the network issue. So let us do the last one. The last option was 4 by 3 comma 1 comma 1. So I'm writing that. Okay, so the last option was 4 by 3 comma 1 comma 1. So let me do that also for you, and then we'll move to something very important for your exam also. Uh, See, once we have done, okay, the last one was 4 by 3 comma 1 comma 1. So if 4 by 3 comma 1 comma 1 belongs to the linear span S, then alpha plus 2 beta should be equals to 4 by 3, alpha plus beta should be 1, and 3 beta should be equals to 1 by 3. So 3 beta is equal to 1 by 3 implies beta should be equals to 1 beta. If 3 beta is equal to 1, then beta should be equals to 1 by 3. If beta is equal to 1 by 3, then alpha should be equal to 2 by 3 from here. And from here you can clearly see 2 by 3 plus 2 by 3 would be equal to 4 by 3. So indeed I can say that my 4 by 3 comma 1 comma 1 is contained in the linear span S. It is contained in the linear span S. I hope it is clear. Yeah, it is indeed a why are you getting confused? Just give me a minute. Okay, so 4 by 3 comma 1 comma 1 also should. Okay, now let us go a little bit further and try to write a few more important stuff. That is a few things regarding algebra of subspaces. I'll leave that for now. I'll straightway jump onto an important portion that is called as the bases and dimensions. And before we do so, let us first define what is linear independence and what is linear dependence. Okay, let us first define that. So let us first define that. What is linear independence and what is linear dependence? Okay. There's a problem with the internet today, so that's why it is troubling us. So just give me a minute. I think let this issue be resolved. I'm going to continue. Okay. Okay. So without wasting time, let us start with linear independence and dependence. Okay. So first thing. Okay. So first thing that you should understand is linear independence and linear dependence. Okay. So here it is. Linear independence. Okay. So if V is a vector space over a field F, if V is a vector space over field F, and if V1, V2, V3, Vn are in V, then we say that they are linearly independent. Yeah, linearly dependent. Let us first say linear dependent over field F if there exist alpha 1, alpha 2, dash 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 alpha n belongs to field F such that alpha 1 v1 plus alpha 2 v2 dash 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 alpha n vn is equals to 0. If you have alpha 1, alpha 2, alpha 3 dash 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 alpha n such that alpha 1 v1 plus alpha 2 v2 dash 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 alpha n vn such that all of them are not 0, all of them are not 0, and still if this entire linear combination becomes 0, then I would say that my vectors v1, v2, v3, vn are linearly dependent. Okay, and if they are not linearly dependent, then they are called as linear independent. And for linear independent, if I'm writing alpha 1 v1 plus alpha 2 v2 dash 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 alpha and vn to be equal to 0, if v1 v2 v3 dash 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 vn are forming linearly independent set of vectors, then alpha 1 alpha 2 all must be equal to 0. That is the only way we can arrive at a 0. But if the vectors v1, v2, v3, vn are linearly dependent over f, then there would be some scalars alpha 1, alpha 2, alpha 3, alpha n belongs to field f such that alpha 1 v1 plus alpha 2 v2 dash 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 alpha n vn would be equal to 0. See, this is quite easy to see. So for example, if I'm saying that in two dimensions my v1 and v2 are linearly dependent, what does it mean? It means there will always be some alpha 1 v1. Let us say I'm talking of two vectors alpha 2, let's meant by linear dependence. That is, if one vector can be expressed as a constant multiple of another vector, then it means that I mean that my vectors are linearly dependent. In other words, if alpha 1 v1 plus alpha 2 v2 is equal to null vector such that alpha i's are not equal to 0, all the alpha i's are not equal to 0, then we will say that v1 v2 here are what you can say v1 v2 here are linearly dependent on each other. Let's say if this is the case and the solution that you arrive is alpha 1 equal to 0 and alpha 2 equal to 0. For this statement to be true, both of the scalars should be equal to 0. Then you will say that v1 and v2 vector form a linearly independent set of vectors. 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 So for example, let's say in two dimensions only, let us consider in two dimensions. What do you think I cap and j cap would be? What do you think I cap and j cap would be? So let us write I cap as 1, 0 and let us write j cap as 0, 1. Now, if they form linear independent set of vectors, then let us write alpha 1, 0 plus beta 0, 1. It should be what? It should be 0, 0. It should be what? It should be 0, 0. If I am saying that alpha this thing and this thing is equal to 0, 0, and let us try to find what it would be. So it implies that alpha comma beta should be equal to 0, 0, and it implies alpha should be equal to 0 and beta should be equal to 0. Only what? See, you can compare the two of the ordered pairs and you can come to a conclusion that alpha equal to 0 and beta equal to 0. What does it imply? It implies that 1, 0 and 0, 1 are linearly independent of each other. Is that clear or not clear? So please do understand what is linear dependence. Linear dependence is when you can express one vector in terms of another vector. Or another way of writing it is that if you can write your v1, v2, v3, if let's say they are your v1, v2, v3 dash 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 vn are linearly dependent set of vectors over field f, then alpha 1 v1 plus alpha 2 v2 dash 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 alpha and vn would be 0, such that all alpha i's are not 0, such that all of the alpha i's are not 0. But if alpha 1 v1 plus alpha 2 v2 dash 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 alpha and vn equal to 0, and it implies that all these alpha i's must be equal to 0, then it implies that v1, v2, v3, vn are all linearly independent set of vectors. Is that clear or not clear? Please do let me know. And we'll do a few examples to understand this concept all the more better. Is that clear? Okay. I think it is clear. Okay, we'll make it clear using some examples also. Okay, so let us do some examples and then you will be able to grasp it all over again. So and this is the main essence that you should keep in mind. Okay, linear dependence and linear independence of vectors is an important concept. Okay, so let us say you have vector u which is 1 comma 0 comma 0, and you have a vector v which is 0 comma 0 comma minus of 5. And now that I'm asking that whether u and v, clearly u belongs to what? U belongs to r cube and v belongs to what? R cube. Now I'm asking, do you think that these two vectors are linearly independent of each other or linearly dependent? So in order to explain that, let us try to find alpha u and beta v and equate it to 0 comma 0 comma 0, right? And if I equate it to 0 comma 0 comma 0, what I'm going to get? Alpha comma 0 comma minus 5 beta is equal to what? It is equal to 0 comma 0 comma 0. And from here I can clearly see that my alpha is equal to 0 and my beta is equal to 0. So my alpha v1 plus beta v2 is equal to 0, gives me alpha equal to 0 and beta equal to 0. That implies what? It implies u and v are linearly independent. Okay, so this is how you do linear dependence. Let us say one more example from, let's say for 4-dimensional. Let me take let us take one u as 1 comma 2 comma 3 comma 4, easy one, and let us take v is equal to 4 comma 3 comma 2 comma 1. What do you think in u and v are? 4 comma 3 comma 2 comma 1. Today I don't know why it is getting stuck, but 4 comma 3 comma 2 comma 1. So this is your v, this is your u, this is your u, this is your v. Now tell me whether these u and v are linearly dependent on each other or linearly independent on each other. So if they are linearly dependent or linearly independent, how to check? We just multiply this with alpha and this with beta and add them up. So what I'll get? Alpha plus 4 beta, directly I'm writing 2 alpha plus 3 beta, comma 3 alpha plus 2 beta plus 4 alpha plus beta is equal to what? Is equal to 0 comma 0 comma 0 comma 0. Okay, if it is the case, then from here I can clearly write, if I do this, if I take these two, if I do if I perform a subtraction, 2 alpha plus 3 beta equal to 0, and from here I can write 3 alpha plus 2 beta equal to 0, and if I subtract them up, what I'll get? I'll get minus alpha plus beta is equal to 0, which implies what? Which implies alpha should be equal to beta, and if I take alpha is equal to beta, I'm going to get alpha is equal to 0 and beta is equal to 0. This is quite evident. So clearly I can say that my u and v are linearly independent to each other. Is that clear? Let us take one more example. We've already written that the set of real functions form a vector space. Okay, so in the set of real vector space of all functions from R to R, from R to R, determine whether sin x comma e की power x is linearly dependent or linearly independent. So what to do? Again, alpha times sine x, let us say it is equal to 0, and beta times e की power x, let us say it is equal to 0. Okay, we already know that exponential, whatsoever be the real number, it is always positive. It implies what? It implies beta should be equal to 0. It implies beta should be equal to 0. Or let us try to add them up and write things up. Okay, so let me write alpha sine x plus beta e की power x equal to 0, right? Now this is true for all x belongs to R. Okay, for all x belongs to R, if I'm saying that sine x and e की power x are linearly dependent or linearly independent, for all x belongs to R, if they are linearly independent or linearly dependent, then alpha sine x plus beta e की power x should be equal to 0. And if they are linearly dependent, then they can be expressed, then alpha and beta should not be equal to 0. And if they are linearly independent, then alpha and beta should be trivially 0. Okay, so both should be 0. So it is true for all real R, so why not place x equal to 0? So if I place x equal to 0, what am I going to get? Alpha into 0 plus beta is equal to 0. What am I going to get? From here I'm getting that beta should be equal to 0. And if beta I'm getting as 0, what does it imply? It implies alpha sine x must be equal to what? Alpha sine x must be equal to 0. Okay, now since this is true for all real R, then x equal to pi by 2, it should also be the case. If I take x equal to pi by 2, I'm getting alpha is equal to 0. Okay, see what we have to see, what we have to write. One thing is very much clear, that if I'm saying that alpha sine x plus beta, if I'm saying that x sine x and e की power x are linearly dependent or linearly independent, then I have to check alpha sine x plus beta e की power x should be a 0 function, right? Here 0 would be a 0 function, right? Now if it is a 0 function, then clearly this should be true for all real R. If it is true for all real R, then it should be true for 0 also, and it should be true for pi by 2 also. If it is true for 0, then beta should be equal to 0. And simultaneously, if it is true for all real R, it should be true for x equal to pi by 2 also. Then for x equal to pi by 2, I'm getting alpha equal to 0. So clearly I can say that alpha should be equal to 0 and beta should be equal to 0. There is no other way out. Or otherwise you also think this way. Otherwise also you think this way. See, if these are linearly dependent, if sin x and exponential are linearly dependent, for all x belongs to R, what does it imply? It implies I can write sin x in form of constant multiple of e की power x, which I cannot do clearly. See, I can never write x. I can find a few points where sin x can be equal to alpha times e की power x, but you cannot be a complete, you can say what you can say. You cannot say that for all real R sin x is equal to e की power x. See, what I am trying to say, if at all sin x and e की power x, sin x and e की power x are linearly dependent, then what does it imply? It implies that this is your sin x. Can I write sin x as a linear combination of e की power x? No, I cannot write that. Right? For a point or two, we can have some kind of equation that, okay, there may be a possibility that they are equal somewhere. But overall, understand sin x can never be written as a constant multiple of e की power x for all x belongs to R. If you could have written this way, only then I can say that e की power x and sin x are linearly dependent on each other. Linear dependence means what? One function can be written as a linear combination of, in terms of constant multiple of another function. Then we say that the functions are linearly dependent on each other. I hope it is clear. Is that clear, Siddhi? Is Siddhi attending the class or not attending the class? Okay. So I hope till now everything is clear. So linear dependence is clear. In easier words, just think what is in easier terms. Just think what is linear dependence. Linear dependence is when one function can be written as a linear combination of another function. You can say a constant multiple of another function. That is the easiest way of expressing the same. Or if you have some if you have some ordered like if you have some elements here like this way, then what you can do, you can multiply. Let's say you have u and v here. You can multiply alpha with u, beta with v, equate it to 0, and see if alpha and beta are both simultaneously coming as 0. If both of them are simultaneously coming as 0, implies u and v are linearly independent. If at all this is not the case, then clearly alpha u plus beta v is equal to 0 implies what? Implies u is equal to minus beta upon alpha times u. So one can be written in some constant multiple of another. So if this is the case, then we say that these are linearly dependent. If one of the element can be written as a constant multiple of another element, then it is linearly dependent. Otherwise, you have to make a check that alpha u plus beta v is equal to 0 implies alpha equal to 0 and beta equal to 0. If it's the case, then we will say that these are linearly independent. Now this brings us to another definition of bases and dimensions. Bases and dimensions. And this is an important okay, so just give me a minute. Okay, so I hope it is clear till now. Now let us move to basis and dimension. This is another important concept that you should keep in mind. Okay, so in R square, if you remember, I told you that both of these vectors, that is 1 comma 0 and 0 comma 1, span your entire R square, right? In R cube, I told you 1 comma 0 comma 0, 0 comma 1 comma 0, and 0 comma 0 comma 1 spans the entire R cube, right? So we can say that all these things like this is named by a special name. This is named by a special name. If you remember, I told you what is a linear span. Linear span is all the possible linear combinations made out of this. So let's say this is S. This is set S contains 1 comma 0 and 0 comma 1. Then the linear span of S would contain alpha comma beta, where alpha and beta both belongs to R. Okay, so this is what I can say right now. Okay, now all these things, I mean this 1 comma 0, 0 comma 1 are named by a special name. Okay, I also told you that if I want to write in this fashion, I can say that this is your I cap and this is your j cap. You can write all the vectors in R square in the form of I cap and j cap. Also, you can say that this generates your R square, right? This generates the entire space R square. Also, you can see that these are linearly independent to each other. See, 1 comma 0 and 0 comma 1 are linearly independent to each other. You just take alpha, just take beta. I took that also for initial assessment. We've already found that alpha is equal to 0 and beta must be equal to 0. So these 1 comma 0 and 0 comma 1 are linearly independent to each other. Second, they span the entire R square. Okay, or we can say that this generates the entire R square. These are called as the bases, and for R square specifically, they are called as the standard basis vectors. Okay, these are called as the standard basis vectors or standard basis. So now let us define with just an understanding. Let me write it more formally. What is basis? So two things are very much clear. That one thing is that these are linear independent to each other. Second thing is that you can span the entire R square, or this can generate entire R square. This can generate entire R square. So a subset B of a vector space of a vector space V, a subset B of a vector space V is called B generates V, by which I mean if I want to take the linear span of B, I must get V in return. So two of the things that are necessary for defining a basis set. The first thing is that the subset B of a vector space V is called as the basis of V if B is linearly independent. And the second thing is that B should generate your V. That is, the linear span of B should be equals to V. Is that clear? I hope it is clear till now. Okay. Now the question arises that whether there can be only two bases. Let's say for R square, can only these two be bases? What I want to say is that are only these two bases? I have told them as standard bases, but are these only bases in which your entire R square can be written? The answer is no. Okay, so I'll illustrate you with an example that R square can be generated even without them. R square can be generated even without them. Matlab means I want to say that I can take other two vectors and I can span the entire R square using those two vectors. Let us take two examples. Let us take 1 comma 1 and let us take v2 as minus 1 comma 1. Now first let us see that whether this set, let me write it as some set B which contains these v1 and v2. Let us first see that whether B, that is v1 and v2, are linearly independent or not. The first condition for B to make a basis set is that whether v1 and v2 are linearly independent or not. Okay, so for that you have to do alpha v1 plus beta v2 equal to 0, and from here you will get alpha minus beta equal to 0 and alpha plus beta equal to 0. From here you will get alpha minus beta equal to 0 and alpha plus beta equal to 0, and it will give you alpha equals to beta, and from here you will get beta equal to 0, and once you get beta equal to 0 you can certainly write that alpha is equal to 0. So clearly v1 and v2 are linearly independent to each other, right? They qualify the first statement. Now will they actually span the entire R square? So for that let us write the span of B. What would be span of B? Span of B would be alpha 1 comma 1 plus beta minus 1 comma 1, where alpha and beta belongs to R. What am I going to get? See, from here it's quite clear. I'm going to get alpha plus beta comma alpha minus beta comma alpha plus beta. Sorry, not this, where alpha and beta both belongs to R. Okay. So clearly, let us write it as delta and let us write it as gamma. So if alpha is real, beta is real, their subtraction would be real. Alpha is real, beta is real, then their addition would be real. So clearly, delta comma gamma will actually span the entire R square, because this is from real, this is from real. So R into R, that is R square, this will completely span the space. Or other way, you can say this way also. If you want to say this way also, you can say that let's say if I want to let us say alpha comma beta be any arbitrary element in R square, be any arbitrary element in R square. Okay, I would say that my v1 and v2, which are actually, we have proven that they are linearly independent to each other, can I write any arbitrary element in R square in terms of V1 and V2. This is the case. Yes, I can do so. See, here it is. I can write alpha and beta as you can say uh, alpha plus beta upon 2 times V1 vector. So this was your V1 vector. V1 vector was what? 1 comma 1, and beta minus alpha upon 2 V2 vector. You can confirm it on your own. You can confirm it on your own. So any vector alpha I cap plus beta j cap or alpha comma beta can be written in terms of v1 vector and v2 vector, where v1 vector and v2 vector are linearly independent to each other. So in this way I can say that v1 and v2 span entire R square. They span entire R square. Are you getting my point? So this is called as a basis. This is called as the basis. So V1 and V2 are forming the basis of R square. If you got the point, initially I referred 1 comma 0 and 0 comma forms the what you can say the basis. Those are called as the standard basis. Another important observation that you should keep in mind is that any subset. So here I'm writing. I mean proper subset. Okay, so no proper subset of a basis. Proper means it cannot be the set itself. So no proper subset of a basis can generate the whole vector space. Now, what do I mean by this? See, let us say I had this thing. Let us take for simplicity 1 comma 0 and 0 comma 1. Okay, let us say this was your set S. I know that this can span the entire R square. It can span the entire R square. But any proper subset, what would be the proper subset to this? 1 comma 0, 0 comma 1, another one would be 5. I'm not interested in that. So let's say these are two proper subsets. If I make a set here, this is a proper subset, one of the proper subset S1, and let's say S2 is this. Then 5 can also be another one. I'm not interested in it. So S1, can I span entire? Can S1 span R square? No, it cannot. Because you know that if S1 is to span R square, then it implies that alpha comma 0 will can if alpha comma 0 can span R alpha comma 0 is equals to what? Is equals to complete R square? No, not. It is for S1 to span R square. There must be possibilities where your y coordinate is non-zero also, no? Because R square would contain all the possibilities of y. Here in S1 you have the restriction that your y coordinate should be equal to 0. So linear span of S1 would be alpha comma 0. It is not equals to R square. Is that clear? Please let me know if this is clear. I hope it is clear. Please let me know if you're getting it, or if there is some doubt, please let me know. Because there is only one concept that is required to be seen. This is called as dimensions. Okay. So the last, the last concept that I want to focus on okay, and another thing that you should remember, this particular set, that is, I'll write it, actually I stated it initially, what is called as a standard basis. So let's say I write it for Rn. So if I'm writing for Rn, E1, which is equals to 1 comma 0 comma 0 dash 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 0, E2 is equal to 0 comma 1 comma 0 dash 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 0, En is equal to 0 comma 0 comma 0 dash 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 1. These are called as the standard basis. These are called as the standard basis of Rn. I hope it is clear. Okay, a few more definitions and results we are going to write tomorrow. But today let us write one more definition, which is called as the dimension of a finite dimensional vector space. So let us first write what is dimension. So what is a dimension? Okay, so if a vector space V over the field F has a basis containing n elements or n vectors, I can say, containing n elements, or you can say n vectors, we say that the dimension of V is equal to n. Trivially, if I'm talking of a singleton 0, this particular vector space, I told you this forms a subspace. This is a vector space itself. Here you can say that the dimension of V is 0. Here you can say that the dimension of V is 0. Further, if a vector space does not have, if a vector space does not have a finite basis, then we say that it is infinite dimensional. So for example, when I was talking about Rn, what is the dimension of Rn? These E1, E2, E3, En are all linearly independent to each other. 1. You can span the entire Rn using these E1, E2, E3, En. So clearly these E1, E2, E3 dash 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 En, that is, these are the standard bases. How many elements are there in the standard basis? N. So what is the dimension of Rn? The dimension of Rn would be N. I hope it is clear. Okay, so I hope that from tomorrow, from tomorrow we are going to, at least I think I will be able to take some quantum mechanics. But overall, I hope all these concepts are clear in your head. Once these are clear in your head, we can go on with some more linear algebra. Because there's a few things we have left in, we have to touch in linear transformation also. Once we'll touch them upon, we'll do something like Jordan canonical forms also. But overall, Understand that linear algebra is an important topic for your development of quantum mechanics. Probably not everything that I'm writing right now is going to come in directly in the examination. These are making your foundations very strong. Once you have a very strong foundation, then uh, nobody can shake you up. So that is one thing. I don't know if I can promise it or not. Probably from tomorrow we may start with quantum mechanics. But even if we don't, we'll do this linear algebra. I hope you're not getting bored in these lectures. I hope you'll continue to come from, further also. Please keep patience. Please revise daily whatever has been done. Till then, take care. Bye bye.